binary operation. So HM, second binary operator, HN, right? Now, you want that element, that result there, you want that to be what this one maps into. So if you map this, you want it to be equal to this, right? So you want f of this to give you this, right? So that's what I'm just saying here, right? So so GI, GJ, and then if you map that, you'll get this HM, filled in circle HN, right? That's what's being said here, okay? But what is HN and HN? Well, GJ maps to HN and GI maps to HM, right? This maps to that maps to that, and you want this, you know, the entry in your group table for group G to map into the corresponding entry in your second group, H, right? So f of this should be what that is. Okay, so you want f of this to be that. But what are these two things? Well, HM is f of GI. HM here is f of GI. Right? And HN here is f of GJ. Right? Therefore, this equals this. Right? And that's, well, it's expressed slightly differently, but that's the main idea, right? Now that constraint, that condition on your function, on your mapping, that by definition is what a homomorphism is. Now, if you added the extra condition that the mapping between the two sets in the groups have to be bijective, then your homomorphism would become an isomorphism. So an isomorphism is like a special case. It's more restrictive than a homomorphism. All right? Okay, so there's the definition of a homomorphism. So between two groups, there's a function, a mapping between this group and this group, between G and H, such that F maps any two members of G into this. Okay. Now let's see. I'll do two examples before I run out of whiteboard. Now here, your G. So I've got X for an example here. So I think this chapter is just full of examples. I think there's eight examples in the chapter, and 3 theorems, I think, and 2 definitions. Well, we've done. This is our first definition here. The definition of homomorphism. Now you're probably quite familiar now with isomorphism. So just think of, as a rule of thumb, think of homomorphism as just an isomorphism with the bijective criterion thrown out. Right? So it should be fairly familiar. It's a more liberal, more encompassing definition than isomorphism. All right. So here's our first example of a homomorphism. And remember, to prove that something's a homomorphism, we have to show this effectively. Yeah? And that's all. Right? We do not have to show that mapping is bijective. Don't need that anymore because it's now a homomorphism, not an isomorphism. Here's the group. It's just a set of integers, so it's an infinite set, and the binary operation is just plus. You're just adding integers, right? And we're going to map this infinite set, in fact, into a very small group consisting of 4 complex numbers, right? So just 1, I, square root of -1, -1, and -I. And the binary operation for this group, H, is just a complex multiplication. Right? The X here is not just amongst real numbers, it's for complex number multiplication. I assume you know complex number theory enough, all right? Okay, so how do we map this infinite set here into this very small group? Well, G is a group under this binary operation of plus. It's a group. Well, here's your mapping function, your f, right? It takes any integer from the set of integers from G, little n is from G, and the mapping is, the function is, f of n is equal to I, complex number I, raised to power integer n. So it's I to the n, right? F of n equals I to the n. Now, why is that function f homomorphic? Well, to prove that this function f of n is I to the n is homomorphic, we have to show this, right? Right. So let's do that. F of m times f of n, using this definition, would be I to the m, I to the m times I to the n multiplied. Right? Now I'm using shorthand notation. Strictly speaking, there's a binary operator in here, and it's of this form. Okay, so these f of m's and f of n's, they are members of H, right? They're one of these four. Okay, because all right. So the binary operation is what? Well, it's multiply. Okay, it's the binary operator of your second group, your H, which is multiply, complex number multiplication. So strictly speaking, there's a complex multiplication sign there, here in the middle, right? But shorthand notation not used. All right. So f of m times f of n is I to the m times I to the n. Now these are just exponents of the same base, so you can rewrite that as I to the n plus n. But what is this? Well, it's just instead of having n here, you've now got n plus n. So this is just the same as f of n plus n, right? And therefore, f of m plus n, or f of mn if you like, because now the binary operation here is this one, right? That's plus in group G, okay? Plus, because there's the binary operation, okay? So you've got that f of mn is equal to fm times fn. There it is. So we've just proven that it's homomorphic, right? This function here is homomorphic. Now, if you want a little bit of analysis, you may ask. Now, this is an infinite set, right? It's the set of all integers, z. Now, which subsets of z map to I, and which subset of z maps to 1, and which subset maps to I, and which maps to -1, and which maps to -I. So the subgroup, in effect, for z, right, we talked about that before. For z is the set of 0, plus or minus 4, plus minus 8, plus minus 12. Okay, so 4z maps to 1, and 1 plus 4z, that infinite subset, if you like, maps to I, and 2 plus 4z maps to -1, and so on. 3 plus 4z maps to -I. Okay, so we've talked a bit about equivalence relations and cosets and stuff, so we can bring in all that terminology and ideas. So here's the Venn diagram of your set z, all the integers, and if you talk about an equivalence relation between any two elements of z, so any two integers, so x tilde, tilde like one wave, x tilde y, so you have an equivalence relation if f of x equals f of y. Right? So x and y are just integers as part of your set, infinite set z, right? Integers. So you've now partitioned, are you familiar with that concept now? You have now partitioned your integers, z, into four what do we call them? Subsets. 4z, 1 plus 4z, 2 plus 4z, 3 plus 4z, and any element in each subset, if you like, will map to the same element of H, right? So, in a sense, these bands here, what's the word? They are fibers, right? We talked a bit about that in an earlier lecture. So we have like here 4 fibers mapping one to one. So that is biject. The fibers map bijectively to corresponding elements in your H. Okay, so and our textbook points out that these are actually cosets. Now this is a group. It's not a subgroup of G, is it? Because these are reals and these are complex numbers. Alright, cosets. Just ordinary think about them, cosets. Cosets in the concept of groups. Now this is not a subgroup of this, because complex numbers, these are reals. I'll have a question mark about that. Anyway, moving on. Alright. Now, like I was just saying before, any two elements